Hey folks, welcome to this episode on equilibrium concentration calculations, aka ice tables, and we're going to be looking specifically at perfect squares. So when we're looking at our equilibrium calculations, we can use something called the ICE method, and stands for initial change in equilibrium. This is when we're given initial concentrations and we're looking for concentrations at equilibrium. So we can use our K equilibrium expression to figure this out. So our I stands for initial concentration, or it could be pressure if we're talking about partial pressures, and it's the initial concentration of all species. Now remember, since this is at the beginning of the reaction, our reaction has not started yet, we'll have products will be equaling to 0 over here. Now our change is going to be happening when we change from initial to equilibrium, and that's expressed using either a minus sign or a plus sign. So usually when we're going to have reactants, reactants will usually be consumed, so they'll be negative, and products are going to be formed in this change period, so they're going to be denoted as a plus. And the magnitude of this negative or positive is going to be based on the balanced equation. So let's say, for example, we had 2NH3 being produced, that's going to be a product, we would have plus 2x. Our variable x will give us some magnitude of change, and it's going to be 2 times based on the coefficient of the balanced equation. And finally, our E is going to be our concentration or pressure at equilibrium. And this is going to be the sum between where it started and the change that occurred. And that's what over here. So if we started off with 0 and we had a change of plus 2x, then our concentration at equilibrium would be 0 plus 2x. So we have 3 different types of questions or situations that can be solved using ICE tables. The first one we're going to focus on right now is perfect squares, but then we're going to move on to ones that we create a quadratic equation with, and then also ones where we can make a simplifying assumption. So how do we do this? Well, to create an ICE table, all we do is we first start off with a balanced chemical equation. We need that to show the coefficients will be our magnitude change. We set up an ICE table. ICE will be the rows. The columns will include the species. We're going to write our equilibrium expression for our balanced chemical equation, and then we're going to just solve for whatever we need to what we need to solve for. Okay, we're going to use our initial quantities when calculating the reaction quotient, which we spoke about before. And that will tell us whether or not the system that we're looking at right now is at equilibrium, or if it has to shift to the left or the right to reach equilibrium. So let's look at this example and work through this. It says the reaction below was carried out at 700 Kelvin. If you start with 1.0 mole of CO and 1.0 mole of H2O in a 5-liter container, how much of each substance is present at equilibrium if K equilibrium is 0.83? Okay, so here we're given an equation. We don't know if it's balanced yet, so let's just take a look. We have 1 carbon, 2 oxygens, 2 oxygens, 2 hydrogens. Okay, we're balanced. So we're good here. Now what we want to do is the question is saying how much of each substance. So that's unless they were saying what this concentration, how much basically either means moles or grams. In this case, we're going to assume it's going to mean moles. We could also do in terms of grams, but let's just keep it at moles as they didn't specify. So we need to figure out how to do this. We need to figure out what the concentrations are of each of these products, all the species at equilibrium. And right now, all we're given 1.0 mole of CO and 1.0 mole of H2. So we're given the initial concentrations for our reactants, nothing for our products. We're assuming that there's going to be 0. So let's develop our ICE table and go from here to see if we can figure out what this change is going to be. So, like we said, ICE goes on to the column. So I'm just going to make species first. So my CO, my H2O, my H2, and my CO2. So we have CO gas, and this is concentrations. Our ICE tables are all about concentrations. H2O, and that's gas. Here I have H2 gas and my concentration CO2 gas. Okay, so these are my concentrations. Now the problem that you might be able to see right away is that we're not given concentrations in the question. We're actually just given moles. So we need to figure out what the concentrations of CO and H2O are first. The way that we do that again is using our equation C is equal to N over V. Our mole for CO is 1.0 mole, and our volume is 5.0 liters. And so what we get here is our initial concentration is going to be equal to 0.20 molar. Okay, so we're going to work with that in a second. Let's just keep setting up our ice table. So I have I, C, and E. Okay, so our initial, our change, and our equilibrium values. So once again, let's go back. Our initial concentration for CO, our initial amount of moles that we had for CO, was 1.0 mole divided by our 5-liter container. We got 0.20 mole, 0.20 mole per liter. And the same thing goes with the water. We have 1 mole here divided by 5 liters. So this is going to be 0.20 molar. Now, our products, since this is the beginning of the reaction, they're going to be 0 and 0. We don't have anything produced now. Now, what is going to be our change? Now, our change is some variable, and it's respective to the coefficient they have in the balanced equation. Now, this is easy because we have all of our coefficients are 1, 1, 1. Now, the change that's going to be happening is going to be x. We're going to call that x. And because this is a reactant, this change will be, or this will be consumed, and we show that using a negative. Now the same thing for water. This has a coefficient of 1. It's being consumed, so it will be x. Our products, on the other hand, are going to be produced. So they are also going to change to some constant here, or x. But they're going to be produced, so it's going to be plus x and plus x as well. Now, just if we had a coefficient, for example, 2 over here, we'd put negative 2x there. So our equilibrium is just a summation of our initial and our change. So in this case, this is going to be 0.20 minus x. Same this, 0.20 minus x. For this, it's 0 plus x. We don't have to write the 0, so all we get is plus x and plus x. So that's how we set up our ice table. Let's go see what we're doing next. So this is our ice table here, just kind of rewritten. What we want to do now is find out the value for x. Now we're going to start off to find the value of x by creating our K equilibrium expression. So K equilibrium is equal to the concentrations of our products over our reactants. And again, only in gas or aqueous phase. Now all of them are in gas phase over here, so we can all write them down and include them in our K equilibrium. I'm going to drop the states just to make it a little bit easier. But usually we're going to be including our states. So our reactants, or our products over our reactants, we have H2 as our product, concentration of CO2 over concentration of CO, and the concentration of H2O. Okay, so now we're going to sub in our values. Now remember also, if we look at the back of the question, it gives us our value for K equilibrium, 0.83. So we're also going to include that in here. Alright, so 0.83 is going to be equal to, now the value for H2 is x, the value for CO2 is x, so it's going to be x times x over, now here we have 0.2 minus x and 0.2 minus x, so that's what we're going to plug in there. 0.20 minus x times 0.20 minus x. Okay, now what we want to do is we want to obviously solve for x. Now, one thing that we notice right away is that here we have x times x, and we have the same sentences, or the same phrases, or the same operations happening twice. So how can we simplify this? How can we take the same operation, simplify it? Well, we can square it. 0.83 is equal to x squared over 0.20 minus x squared. Okay, so kind of if we were given this here, we could kind of break it apart into this. So we're doing the opposite. We're condensing it and saying these squares. Now, once we have these squares, this makes life so much more easy because since both the top term and the bottom term are squared, we can square root it and get it just to x. So I can square root this side, and what I do to this side, I also have to do to this side over here. So if we square root both sides, what we end up getting is we get 0, it's right here, 0.911043 is equal to x over 0.20 minus x. Alright, that makes it so much easier. We don't have to create a quadratic equation for this because we don't have any squared x's. So to isolate for x, we're going to bring this up to this side over here, multiply both sides, and then we're going to bring all the x's onto one side and solve for x. So the way that we get that, we're going to get 0.911043 times 0.20 minus x, and that's going to be equal to x. In this case, that if we FOIL that out, we get, and I'm just going to move it to the other side right at the get-go. So I'll get 1.911043x is going to be equal to 0.182009. All right, so again, what I did there is I just FOILed this in, that multiplied this, and multiplied by that. Then I took the term with the x and brought it over to the same side as the x, and I got that. I added them up, and this is where I get here. So now, to isolate for x, I divide both sides by 1.911043, and x is going to be equal to 0.09534. So there's our value for x. Now, using this, we're going to have to figure out what our eventual equilibrium concentrations are going to be. So now that we know that x is equal to 0.09534, and this is a change, this is also going to be in mole per liter, we can figure out what our concentrations of our reactants and our products are at equilibrium. How do we know this? Well, we have our equations that include x. So for our reactants, we have 0.20 minus x for both, and then for these we have plus x. Now, one thing is, remember that it's asking us for how much of the substance. So eventually what we're going to have to do, remember that we said that these are going to be moles, we're going to have to go from mole per liter into moles. So let's first figure out what the concentrations of our reactants are going to be at equilibrium. And the way we do that is we have 0.20 minus x. Now x is the value that we found before, 0.09534, and we get 0.10460 mole per liter. Now to get from mole per liter into moles, we have to use our C is equal to N over V and rearrange to find N, which is C times V. So if we get our 0.10460 mole per liter, and we multiply it by our volume, which again from the equation is 5 liters, our liters cancel out, and we get 0.5233 mole. To see significant figures, we get 0.52 mole. So there's our answer for our reactants. Now both of them, and that's for our our value for CO and for H2O, because both of them have the same equation. Okay, so we just kind of save some time there. Both of them have this 0.20 minus x, and so we just used it for the same thing. So now let's see what our equilibrium values are for H2 and CO2. So the concentration of H2 and CO2 both equal x. Okay, so we already know what x is. X is going to be 0.09534 mole per liter. But again, it's asking us for how much in terms of moles, so we're going to have to multiply this by 5.0 liters. Our liters cancel out, and we get 0.4767 mole. To two significant figures, it's 0.48 mole. And that's the amount for H2 and CO2. So there we have it. We figured out at equilibrium that we have 0.48 mole of both H2 and CO2, and at equilibrium we have 0.52 mole of CO and H2O. And that makes sense if we go back to our K equilibrium value. Remember that for this K equilibrium value, for it to be a decimal, what that means is that our numerator has to be bigger than our denominator has to be bigger than our numerator. And remember that our denominator is all about our reactants, and our numerator is all about products. So at the end, what we should have is we should have a greater concentration of reactants than we have products for this number to be a decimal, and we do. Now this is again in moles. If we go back to what our concentrations are, 0.1046 versus 0.095, we can see that we have a much larger concentration of reactants than we do of products, and that makes sense because that would give us a value of 0.83. So that's how we attack perfect squares. Again, the main thing here is seeing if we have repeating operations. We saw x times x, and we also saw 0.20 minus x times 0.20 minus x. And the way we can simplify that is by squaring it and then square rooting it. So if we're able to do that, that's the best way. It saves us from doing a quadratic equation. Next episode, we are going to be looking to see how do we do something if we just simply cannot get a square root of that, and how do we approach it if we have to form a quadratic equation. So thanks very much for watching. See you next time.